Hello everyone, hope all of you are well. So on some requests from a couple of students, I'll be doing this video. And in this video, we are going to talk about some marks that you should always score. And in these always score marks, we are basically going to talk about like commonly tested definitions, commonly tested like things about the units and so on and so forth. Right, so we'll be going exactly in the order which is specified by our syllabus, and we will be talking about what are the things which are always asked in the same way and how you can secure those marks and have them in the bag. So first off, let's start with basically our unit 1, which is like forces, motion and all of that stuff. This unit I like to call mechanics. And even in mechanics, I'll be going in a very chronological order. So the first chapter is physical quantities and measurements. So in this chapter, a lot of the stuff is something which is not really something that you can memorize in a certain way. It's going to be tested in different ways. But something which is always tested the same way is this idea that what is the difference between scalars and vectors. So what's the answer to this? So the answer to this question would also be the same. For example, if you are asked to explain the difference between scalars and vectors, or distance and displacement, or speed and velocity, which is that the scalar quantities don't have direction. So similarly, distance and speed don't have direction, but the vectors, displacement and velocity do have direction. Another one which is commonly asked and more or less always in the same way is how do you measure the time period of a pendulum? So the answer to that question is this, that you measure 10 oscillations 3 times. So you're measuring the time not for one oscillation but for 10 oscillations, and you don't do that once either, you do this 3 times. Then you average the 3 readings that you get. So first time for 10 oscillations, the second time and the third time for 10 oscillations, you average these out and you get the average time for 10 oscillations. And because you want to find the time period of one oscillation, so you then divide by 10 to get the average time for one oscillation. So this is what is asked in physical quantities and measurements in that first chapter. Let's talk about the second one. So when we talk about kinematics, you have a lot of definitions here in this chapter, which you must know. One of these is the definition of speed, which is given like this. So the proper definition for speed is this: the rate of change of distance, or another one correspondingly could be the change in distance over the change in time. I generally do not recommend the distance traveled per unit time, and this is sort of like a gray area in your syllabus, because sometimes what they talk about as distance traveled per unit time, that fits more in the definition of average speed. So speed is the rate of change of distance. Similarly, if we talk about the corresponding quantity of velocity, that can be defined as the rate of change of displacement or the change in displacement over the change in time. So again, you do have more ideas here, but because that's always asked in some different ways in this chapter, such as the ideas regarding gradients, uniform, non-uniform accelerations or speeds, so I'm not including it as a part of this video, but it is very much part of your syllabus, and it is actually most of the questions are related to those ideas. All right, let's go on to the next chapter that we basically have, which is mass, weight, density. So the definition of mass is also now very precise with your new syllabus. So for mass, this is the new definition that you should know, which is the measure of quantity of matter, and this is also something that we had before. But now the new phrase that you must remember is that this is for an object which is at rest relative to the observer. So now with this new specification, if you do not say this word, you will lose marks. And about the mass, we also know this, that the mass leads to another property which is called inertia, which is Basically the idea that an object resists changes in its state of rest or motion, whatever it is in. So weight is obviously the gravitational force, so it's not really asked as a definition. What is asked as a definition is this: the gravitational field strength, which is really known as small g, and this is defined as the force acting per unit mass. In the form of an equation, it looks like this. So either you might have this written as F or as W over M. Hence the equation W equals to mg. Another term which is related to the ideas of gravity is a gravitational field. Just the gravitational field, not the strength, is defined like this: is that any field is always a region of space, but what differs is what causes the object to experience a force. In the case of a gravitational field, it's the mass which causes it to experience a force. On to some more ideas. So now we're on the idea of density. Again, this is really straightforward, and this is just the mass per unit volume. Again, more ideas are related to the ideas of how to measure density for liquids and regular and irregular solids. So the next idea is, now it's the start of the unit on forces. Again, with forces, please do remember that there will be other content which could be tested in different ways to what we're doing right now. So one of the common things which could be asked with forces is the idea of Newton's first law. Again, before this, you have ideas of free body diagrams, how you talk about those different forces. But that's not something which is going to be asked in the same way always, which is that an object remains at rest or it continues to move with constant speed in a straight line. And these two things really mean with constant velocity, unless acted on by a resultant force. Next one is Newton's second law. And for this, you don't even really need to know any such words that you had to know for the first law. You just need to know this equation, which you obviously already know. But just for the record, here it is, F equals to ma. You just need to know that F is the resultant force, m is the mass, a is the acceleration. Newton's third law as well, you do need to know exactly how to describe this. Newton's third law now. So Newton's third law is when an object A exerts a force on object B exerts an equal and opposite force on A. Please do not write an action as an equal and opposite reaction anymore, because that's something the examiner will not be accepting now. Because it does not show one really important aspect of Newton's third law, which a lot of people also tend to forget, is that both of these forces act on different bodies. There are really three types of things that you must remember for your board, which is that the forces are equal in magnitude, they're opposite in direction, and you guys do remember this. But what you must also remember is what one exerts as a force on another, the other one also exerts on the first one. So regarding friction, we have some ideas here as well. So one of the first ones you obviously know is the idea of the thinking distance. The definition of this is often asked, as well as questions with calculations. So the thinking distance is defined like this: the distance traveled from the time that you identify a hazard to the time that you actually apply the brakes. If you're looking at mark schemes for older papers, you might also see this. That is the distance traveled during the reaction time. The next one, then you can also probably guess what's coming up now, is its counterpart, the braking distance. So the braking distance is the distance traveled between applying the brakes and your vehicle then coming to rest. The next one is obviously the stopping distance. And the stopping distance we know is the sum of the thinking distance and the braking distance. So this is all from the start to all the way till the end. So this is the distance traveled between identifying a hazard till it actually coming to rest. So this obviously includes a part of the braking in the middle too. Then we have the topic on springs. So something which is asked pretty often is the idea of the spring constant, and a lot of the time you also have to use this in calculations in both MCQs as well as the structured questions. So this is defined as the force required per unit extension. If you look at the equation, if I just write it out here for you, K equals F over X, the symbol of the spring constant is K, so it's the force required per unit extension, and in a way it's really similar to the equation that defined the gravitational field strength. Another term that sometimes you have to locate on a graph, sometimes you might just be asked to talk about this, is the limit of proportionality, and that's defined like this. So the limit of proportionality is the load or the point after which, so this thing is important, it's after the force is no longer proportional to extension. So this equation really shows us the direct proportionality between force and extension, but that's only valid up to the limit of proportionality, after which force and extension are no longer proportional. The next chapter is circular motion. But you don't really have something which is assessed as part of theory as a definition or as a common term a lot in the papers. So we go on to the next one, which is the idea of turning effects. So often you will be asked just to define the moment or the turning effect of a force. So how do you define this? So it's the product of force and the distance of the force from the pivot. Usually this is for 2 marks. One is just for saying force and distance in some way, and the next mark is for elaborating more on the distance, which is of the force from the pivot. So also remember, if you have to write this in an equation form, let's say you write it like this, if you write it as F times D, you do need to explain, if the terms have not been already used by the examiners, what the force F, what the distance D stands for. The second thing which is usually asked in this chapter is the principle of moments. So for this one, again, this is something which is really frequently asked. You say that for an object in equilibrium, if the examiner has already not stated in the question that's, for example, if it says state the principle of moments for an object in equilibrium, then you don't need to say this again. But if he hasn't, you have to say this. And then the next thing you say is that the total, or you can use the word resultant moment, is 0. Or you can also use another variant of this statement, which is that the sum of clockwise moments and the sum of anti-clockwise moments are equal. But this is obviously the shorter one to write, also helps you save up a bit of time. While we're on the topic of moments, something else which is commonly asked is the center of gravity and its definition, what it means. Alright, so the center of gravity, this is the point through which the entire weight of the object, and this part is really important, this is assumed to act through this point. This is not really the point through which it acts. And similarly, if you talk about center of mass, definition would still be the same, right? So do keep this in mind. So this is on the idea of the turning effects. Next we have questions related to momentum, and obviously the first thing which is asked with this chapter is the definition of momentum itself. Again, really straightforward. This is just the product of mass and velocity. If you also want to write it as mass, and then you put in a cross for the multiplication sign, and if you say mass times velocity, that's also fine. The examiner will accept that as well. Similarly, you may be asked to define the resultant force as well. And resultant force, do keep in mind that it's not defined according to F equals to ma. Rather, it's defined by this equation. So it's defined as the rate of change of momentum, and the equation looks like this: delta P over delta T. If you rearrange this equation, you get another important term which might be asked, is known as impulse, which is the product of force and the time for which the force acts. And impulse is just another word for the change in momentum, and that's just F delta T, just a simple rearrangement of this equation. There is also a law in this chapter, which is the law or the principle of conservation of momentum. And this is also something that you're asked really often. Like this, that for a closed system, you can either say this or you can say that no external forces act. I prefer this one. You say that the total momentum is constant, because conservation means something is basically conserved, which means it's constant. And pretty similar to how we had the principle of moment, you can also say this in another way. If you say that the total momentum of the objects before the collision is equal to the total momentum after the collision. That's the same thing as what you say here. So momentum is also done. Let's move on to work energy power now. So the first definition in that chapter is obviously work done, to be more specific. So it's the product of the force and the displacement moved in the direction of the force. Again, if you write this down in a formula as this, if not previously specified by the examiner, you need to show what each of these symbols stand for. So energy is not a definition as a part of your new syllabus. It's rather now talked about in terms of energy stores. But something which is still asked as a law is the idea of the conservation of energy. And again, we just had a look at a law which was also a conservation law. That was conservation of momentum. This is conservation of energy. So you say the same thing, that the total energy is the same, but additionally, so energy cannot be created nor destroyed. This is something you need to say as well. And it is transferred between stores such that the total energy is constant. Again, things which are really the heart of this chapter, which is kinetic energy, potential energy, don't have the same type of question being asked all the time for it. So then we move on to the idea of energy resources, but in that as well, questions are usually very different. Something which I feel is something which is not really asked all that often, but it could be asked, and I've seen people messing this up the few times it has been asked, is the idea of what it means to be a renewable resource. So this is an energy source that does not run out, right? This is what it means for it to be renewable. The next thing we should know how to define is efficiency as a term. So it's the ratio of the useful energy output to the total energy input. Saying this word useful is something that the examiner does require you to mention, right? And you obviously know the equations as well. And again, you don't need to make the symbol. I just like it because it's cool. So you have the ratio of the energy or the power output over the energy or the power input. The squiggly lines are just showing it could be output, it could be energy or power, and sometimes you're also required to multiply this by 100 to convert this into a percentage. Next thing is the definition of power. So you can say either it's the rate at which energy is transferred, so the rate of energy transfer, or another way, because energy and work are basically the same thing, you can also say it's the rate at which work is done. So it's written like this, E, or instead of this, you can also write this as work over time. So that's all of work energy power. Let's go on to pressure. So in pressure, something which is asked often is just this idea of pressure as a definition, which is the force acting perpendicularly per unit area, or in the form of an equation, P equals to F over A. So again, you guys have more things like the liquid pressure and stuff like that, but another thing that will now start to be tested in the upcoming sessions, because this is a recent addition to the syllabus, is this, which is that you may be asked to, first of all, you sometimes may be asked to state this given some experiment, or the other way around, that you should have to describe an experiment to show that the pressure produces a force at right angles to the surface. Which is that if you have a container which is full of a liquid, and if you have a hole in this liquid here like this, the water is going to emerge in a direction like this. But if we just look at the angle that it makes right when it emerges, so it's perpendicular to the walls of the container. So now we go on to unit 2, basically the unit that is related to all of heat, and then we'll see what are some commonly tested questions there. So now we're talking about the unit on heat. So with the unit on the kinetic model of matter, which is the first one, there are some questions which are asked time and again. The first one which is asked is often related to the idea of absolute zero. And this temperature is also asked, and you are also supposed to explain this. So the temperature in degrees Celsius is minus 273 degrees Celsius, or you can say this is 0 Kelvin. And the significance of this point is that this is where the particles have the least kinetic energy. Do note what I say here, it's not zero kinetic energy, rather it's where they have the least kinetic energy. And you must also talk about this exactly when you are also asked in a question. Another question which is asked really often is this, that how do particles, for example in a gas, produce pressure? Again, a lot of people for some reason mess this up, even though it's not really as difficult as you might think it is. So with this, you really need to talk about this in terms of these 3 points. The first one is that these particles are in constant random motion. So they're always moving. Because of that movement, they can collide with the walls. Now here, this is important to keep in mind that the collisions are with the walls and not among the particles themselves. And then as a result of those collisions, they exert a force leading to a pressure. Also keep in mind that sometimes maybe, just maybe, the examiner could ask you how this links to the idea of momentum. And this is just an idea. Then you would say this as well, that because of the collisions, there's going to be a rate of change of momentum which leads to a force. So in this one, you don't need to talk about the increase in volume or the increase in temperature or whatever that causes. How does that affect the pressure? You just want to talk about how that pressure is produced. Another common question which is asked a lot is the idea of the relationships among these variables. But always remember that when we have to talk about the relationship between these 3 terms, PV and T, so this basically forms a triangle like this. Whenever we talk about any 2 relationships, the third one is going to be constant. So if you're talking about PV, temperature is constant, PT, V is constant, VT, pressure is constant. So for example, if we first talk about the relationship between pressure and temperature at constant volume. So this is the explanation in this case. First off, for example, if the examiner says what's going to happen if the temperature increases. So first off, you should link this with the movement of the particles. So kinetic energy should increase. As a result, the particles are now moving faster, which leads to more frequent collisions. More collisions is strictly speaking not correct, so you should say more frequent collisions, which cause a greater force, and hence that causes the pressure to go up. If they talk about a decrease in temperature, you just have to flip this entire reasoning. Similarly, if we talk about volume versus temperature, and now you guys know that pressure is going to be constant. So with volume and temperature, again, if we're talking about the impact of temperature, the first fact is going to be the same. The temperature increases, so kinetic energy also increases. But previously I was saying particles move faster, right? So if you look here, I was previously saying particles move faster, but now I'm going to say they move further because I have to link this with the idea of volume. So since the particles move further, they spread out to occupy more space, and that's how volume goes up. Third relationship is PV, for which you also have the equation. So P, pressure versus volume at constant temperature, just shown by this equation as well. So for this one, we start with the idea that if the volume is decreasing, the particles move closer together, and that leads to more frequent collisions with the walls, and again, exactly as what we discussed here, a greater force leading to the pressure going up. Do make sure that here you would not say the particles move faster, because how fast a particle is moving depends on speed, which is really kinetic energy, which depends on temperature. So that is like the biggest blunder you could make. Often with the usage of this equation, you will be asked, what are the two conditions required for this equation to be valid? And one condition we just talked about, that the temperature needs to be constant, but another one is to say that the mass of the gas is constant. So that's about the kinetic model of matter, what's asked most. So now we're on to the thermal properties of matter. Regarding this, something about the expansion is often asked, especially the order of expansion of all the states of matter. So the expansion is greatest in gases, least in solids, and you'll often be asked reasons for this as well. So in gases, the intermolecular forces, IMF means that, are the weakest, so you have to do the least work in increasing the spacing of particles. So then there's obviously the conversion of Celsius and degrees Celsius. But something else which is often asked for definitions, and people somehow still mess this up, is the definition of specific heat capacity, which is the energy required per unit mass per unit temperature rise. If you want to switch around their orders, it doesn't make any difference at all. This is the equation which defines it. So energy, whatever comes after the per unit, is basically in the denominator. So per unit mass, per unit temperature, so that's also in the denominator. Something else which is super important in this chapter is state changes, and the energy that we use to talk about that is latent heat. This is literally the only thing which is related to latent heat which is still left in the syllabus, which is this. So you just need to know now that the energy required for state changes is known as latent heat. How you can remember this is latent means hidden, and why do we call this hidden is because it's not visible as a temperature change. And the idea behind this in terms of particles is that this does work against those intermolecular forces of attraction. Evaporation is the next thing, and even though it's really easy, you have just the same questions popping up all the time. You just need to know the answer to these. So regarding evaporation, you should obviously know the idea of the more energetic particles escaping from the surface of the liquid. And related to this is the question as to how does evaporation produce a cooling effect. So the idea is that the more energetic particles leave, which means that the higher kinetic energy particles have now left. Particles which are left behind have less kinetic energy, hence a lower temperature as well. Something else which is commonly asked here are the factors which affect the evaporation. In fact, let's say the rate of evaporation, how fast this happens. So the factors are temperature, surface area, and the presence of a drought or a wind. If you have a greater temperature or a greater surface area, both of these will increase the rate of evaporation, and similarly if you have a wind blowing, that's also going to increase the rate of evaporation. It also helps that if you can explain this in terms of the particles, then it's really easy to do once you know exactly what happens in evaporation. For example, if somebody just comes up to me and says to me that explain how increasing the surface area increases the rate of evaporation. So I would just say that more of those high kinetic energy particles are now exposed to the surface, so the rate of evaporation would go up, right? So you just need to be like very flexible with the questions that can come your way. Next common idea, and it's still related to evaporation, are the differences of boiling and evaporation. So with boiling and evaporation, one of the main differences is that boiling produces bubbles, evaporation doesn't. Boiling only takes place at a fixed temperature, whereas evaporation can take place as long as the state of matter is a liquid. The third difference is that boiling takes place inside the entire liquid, whereas evaporation just takes place on the surface. Let's now go on to the third chapter, which is transfer of thermal energy. So when we talk about the first method of thermal energy transfer, which is conduction, that can be split into two mechanisms, which are molecular vibrations and free electron movements. In the cases of non-metals, you know that this is going to be the more dominant method, but with metals you have the free electron movement as the dominant method. And this is what you say in each point. In the case of molecular vibrations, you start off with this idea that kinetic energy increases so that the vibration is now faster, and because of collisions with their neighbors, the molecules pass on some of their energy to them. In the case of free electrons, you start with the same idea that the electrons basically gain energy from that heat source, and because they're not restricted in their place, they can travel throughout the length of that metal. The third point is the most important to say, which is that electrons, when they go on to the colder end, they pass on the energy to the atoms there by colliding with them. So on to the next method of energy transfer, which is convection. In convection, your answer should always be exactly in this flow. That first you talk about what's happening to the temperature, then you talk about what's happening to the volume, then you talk about what's happening to the density, and finally you then comment on whether this fluid is going to rise or sink. So whatever happens to the temperature is also going to happen to the volume. So for example, if temperature goes up, volume is also going to go up. But because of the density formula, m over v, the density is going to go down, and hence if the density goes down means this is now lighter, so it's then going to rise. And then similarly it would be the opposite case in terms of something being cooled. Always remember that in questions related to convection, you do have to refer to the term density one way or another. So often in one way or another, you'll also be assessed on the ideas of air pockets and how they reduce heat loss. So the idea is that air pockets reduce heat loss because of both conduction and convection. Conduction because air is a poor conductor, or you can say a good insulator, and convection because the air which is now trapped cannot participate in the setting up of a convection current. The last method of thermal energy transfer is radiation. Do keep in mind that you should always mention the entire term, which is infrared radiation, along with it. Sometimes you have marks for just mentioning the word infrared as well. In many different scenarios, this idea will be assessed that radiation is the only one which takes place in a vacuum. This might be asked, for example, when talking about the energy transfer from the sun, or for example, if you're talking about a flask, does the air pockets in that case reduce radiation? And the answer is no, because it takes place in a vacuum as well. So then you leverage the texture and the color of the surfaces to control radiation.